Am I on? Yeah, all right. Wow, I really can't see much of the audience from up here. Okay, so thank you for the introduction. Yes, my name is Melanie Warrick. I work at SkyMind. I am hashtag I look like an engineer. And we don't currently use attention models where I work, but it was a topic that I saw someone present on, and I thought, this is interesting. I think I want to learn about it. And I have a habit of presenting on things that I want to learn about, so let's all learn about this together. Okay, so how many of you actually use neural nets right now? All right, I see some hands. That's good. So it seems to be the topic of the day. Almost everybody has at least mentioned neural nets or deep learning, which they don't necessarily go exactly hand in hand, but close enough. So attention models is this concept that, to a degree, is a little bit new, has been out recently, and in terms of the last couple of years, there's a lot of papers that have come out, but it's not fully new. It's been around for a little while, actually. So what I want to do is try to give you guys a little bit of an overview of what attention is as it relates to neural nets, to help you understand this concept of soft versus hard and what that means. I'm going to give an example of a hard attention model as it relates to computer vision, and then touch briefly on the learning rule, which is used with hard models in particular, as well as talk a little bit about performance as it relates to this example that I have. So let's go into the details, and the way I'm going to present this is talking about the data from a visual perspective, because I think that's the easiest way to think about attention. From a visual perspective, but it doesn't mean that you can only use an attention model or models with visual data. You can definitely use it with all sorts of data. So when you look out, or when you look at anything, you see, there's something in front of you that you will see, and you will take in the data, but you don't necessarily perceive it all at the same time or in the same way. Especially if you're looking for something in particular, you might actually scan through the crowd and really look for maybe a red hat or something along those lines, or your friend. You're doing facial recognition yourself, and your eyes are perceiving the world in front of you and processing the data, but not really fully processing everything all at once in terms of the details or the information that you're trying to process in your brain. And so when you look, you have an ability to do your own filtering and focus and provide some level of attention to what you're consuming in your data. And that's what the attention model is about. It's trying to help provide some level of input focus in terms of, I have a lot of data. I don't want to overeat and overconsume all this data all at once. I want to, prioritize it. The other thing to think about, and a lot of the papers that I was looking at in the last couple of years that have come out on this topic, talk about attention from a perspective of sequence, prioritizing the data in terms of the order in which you try to process it. It doesn't have to necessarily be sequential, but I think it's an easier way to try to think about how to approach this model. The heart of it, I think, is it's about context. It's about helping to provide some additional context about the data that you're trying to process. And you can almost think about it along the lines of feature engineering, giving some additional feature focus. And the weights are what you change. With any model that we do, any model that we build, we're always using our weights, our coefficients, to help apply that model and make it fit whatever question we're trying to answer. So that's what you're going to use to make your retention model, of course, better focus. Okay, so I kind of skipped through this really quickly, and I know I've already said that this is related to neural nets. And we've obviously already heard a lot about neural nets and also a little bit about attention models, but just to sort of backtrack and make sure we're all on the same page here, we're talking machine learning algorithms that do classification and prediction, right? So when you use the attention model, and you are trying to do some level of classification and prediction, and when you do any kind of, looking at an image, an object, you're going to specifically do a couple different types of ways in which you will grab the data. These are some techniques that are straight out of just general attention, and the way that you would grab this data is you could easily say that you take a full image and you crop certain sections out of that image. You could even, and that would be the same thing as taking the margin or defining a margin around that. You can also have higher resolution. You can have higher resolution in certain areas and lower resolution in other areas to differentiate between that fringe and the focus. And you can do something with zoom where you could actually consume maybe the whole image all at once with a much lower resolution, but to get a general sense of some very summarized objects in the space. Let's say you're trying to read labels on a can, but first you need to find out where the can is. So you get a very low resolution image, find the outline of a can, and then you can start to zoom in and increase the resolution on that image to be able to get the words off of the can. So those are some ways in which you might consume the data when you're working with an attention model. And what the attention model is trying to help you decide, because you're usually trying to get something out of your model, is where to look. Or if you're not necessarily using images and you don't want to think about it as where to look, what data to consume next. Most models are trying to help you decide, what actions to take, what classification, how to classify things. The attention model, it's going to help with that as well, but its main goal is to try to figure out what data do you want to take in next. Now, there's this concept of soft and hard that has come out around attention models. And I was talking to some of the people I was talking to about this was telling me that this is kind of a new idea. And it's not necessarily a very hard and fast rule in terms of the differentiation between these models. But the main differences, why they're trying to classify attention models with soft and hard, is because of the way you consume the information, the way you consume and take in an input, and how you update your weights, how you go back into the model and you change the weights to make the model a better predictor. In terms of the soft model, it will take in and it will have an understanding of the full input space. It will be able to model the full input space. And because of that, it can then estimate all of the expected output. And thus, it makes it differentiable. And that means you can do backprops. If you've worked with neural nets before, you've heard of backprop. I know we already heard a talk about backprop. That is a standard technique you would use to update weights. Whereas with a hard model, you're not going to necessarily take in the full input space. You may not be able to understand the full state of which you're working with. You may not be able to, or you may not want to fully consume the input space. And so you'll sample it. But because you're sampling it, and you're usually using a stochastic technique to sample it, your output is not necessarily deterministic, or it isn't deterministic, and thus it's not differentiable. So we'll use techniques like policy gradients to be able to make it differentiable, combined with a variance reduction, usually, to be able to allow you to go back and make updates to your weights. So those are the main sort of things to think about when you're talking about soft and hard. And I pulled out one of the papers that's sort of the short name for it, Show and Tell, which describes the differences between soft and hard models. This is an image, or an example of an image out of the paper where they're trying to give you a sense of how, when you're reading images, what that might look like between the two different models. And the white areas where they're focusing, well, the way to think about this is that in the top example, they're consuming the whole image. They're just putting different levels of priority in terms of all the pixels that are being brought in. And so there's a higher weight, a higher emphasis on the white areas. While in the bottom example, there's a cropped circle. That is the data that's being brought in. That's the information that's being consumed. It doesn't change in size, and it just changes in the location where it's bringing in the data. So with the soft attention, the value you're going to get from this, because you're taking in the whole image still, is that you will become a little more context aware of of the data that you're working with. You will be able to understand it and have a better sense of what kind of information are you getting out of that data space, and where would you want to focus, because you have an understanding of the full input space. The challenge you have here is because if you notice that the white area that I was showing you, and let's see, can I go back? Yeah. All right, so the white area that I was showing you on the top shifts and changes. It doesn't have a set, defined amount of input that it'll take in. So there's potential scale limitations with this by trying to consume all of the input space. It can take a lot more resources to be able to compute that actual input and be able to have some kind of results out of it. While the hard model, it decouples the size of the data from the actual number of computations that you're doing. And so the value with that is that, you might actually be able to work with smaller resources. You might be able to work with one server to be able to process your data set. And the problem that you will hit up against there is that if you don't have the right level of context to help guide where to look, you could spend a lot of time, a lot more time trying to figure out where to glimpse, what to look at next that will give you some valuable information about the data you're working with. There's a number of different models that have been described in these papers that I came across. Well, I didn't just come across, I looked at these papers. That there's a number of different models that have been described in the last couple of years. And this is just sort of a listing of the ones that are some of the key ones out there, and to help give you a sense of how to think about them between soft and hard. And by the way, I have already tweeted out this a link to where this deck is located if you want to reference that. And my Twitter handle's on the corner. So all of those models, the main things that they're achieving or the main things that these papers have been doing with these models are things like reading and writing to memory, generating images, generating language, classifying, various objects, using them to actually do descriptions for images. And I have no doubt that this is being used with robotics. I was fortunate enough to talk to a few people who are actually trying to apply this in the real world to things like medical imaging and to license plate recognition. So there are there's some definite value to using this model to solve problems and to provide some additional heightened performance in the models that people want to apply to real world problems. The other thing I want to make sure I note about this is that recurrent nets are the ones that are being used primarily for attention models, or in the hard attention models, and I'm going to touch on that again in a minute. But you can actually couple this with things like autoencoders and other types of neural net models, so don't think that LSTMs are the only thing that you can use with an attention model. Okay, let's talk about hard models. So hard models in computer vision, the multiple object recognition with visual attention paper had a good example of a hard model that they used called the deep recurrent attention model. It was based off of another model that was the recurrent attention model. Anyways, it's a recurrent model with attention that they used to read house address numbers. So there's a great data set that exists that they used to work with that. So to better understand this, let's briefly step back and say, okay, so convolution nets. If you've done anything with computer vision and neural nets, you've heard about convolution nets. These are sort of the go-to neural net for doing any type of image analysis. And when you do anything with convolution nets, you're usually using some kind of kernel, and it's kernel of weights or a window of weights. It's a small little subset there. That's the center little square that you see. And it's moved across the whole image to do a weighted sum to be able to reduce it down to more salient features. Now, that kernel, as I mentioned, gets moved across the whole image. So the number of computations that are being done, and this is just me re-emphasizing the point I made earlier, the number of computations will increase as the image size increases. So if you start with something that's 28 by 28 pixels and you go up to 200 by 200, you definitely increase those number of computations. Well, as I mentioned, the hard model has this constrained space. It says, I'm going to only take in this amount of pixels each time I glimpse at something, and that is not going to change despite how big or how small this image gets. Now, granted, you could spend a lot more time looking for something if the image gets bigger, and that's where the context part comes in. Now, the other part that you'll see, especially in the hard models in these papers that have come out, is that they're coupled, as I mentioned, with recurrent nets, and specifically with LSTMs. And so this is just a very simplified version of the recurrent net. I like the way they explain how, this is one neuron or one node, and how if you see there's an x1 or xt minus 1, xt plus 1 on the bottom there, and that's just showing that there's this input coming in at different time steps. And so what it's doing is it's saying, okay, I've got this new input, but I'm looking back at the W that's coming in terms of saying, what did I know before? What have I seen before? And I'm keeping track of that, and I'm feeding it back to myself each time so that I can improve upon what I'm looking at, because I have a history, I have a state that I can retain about what I know about my space. And this is very valuable for hard models, especially if you only have samples of what you're looking at. So the general goals for any kind of model that you're going to work with is going to be to minimize your error and maximize your reward. And some of the challenges you're going to be up against potentially is that it can be sparse and delayed. But that's a general goal for any model you build, and it's especially true when you start to talk about attention models. Most of them will talk about it from the perspective of trying to improve your reward. So the deep recurrent attention model, it's actually coupling a number of different types of models together. It's got a convolution net that's bringing in the actual sampled glimpsed image. It's got two recurrent nets, one that is doing classification, that's the lowest one, and the one on the top is doing the actual location identification. And so on the top one, as it's reading in the information, it's reading in like, it has a supervised model that it's working with, and it's saying, okay, I did classification, did I get it right? I'm going to feed that up into my recurrent net that's going to figure out where I'm looking next, and that will be used as its reward to figure out what to look at next. In addition, it's using this context about what it looked at before and the reward to be able to say, let me figure out what's my next coordinates for this image. And it's using this reinforced learning rule. The reinforced learning rule is a policy gradient learning rule that's pretty common in a lot of the papers that I came across. Monte Carlo's policy gradient in particular. This is a very basic version of it. The paper actually is a little bit more complex version, but Williams apparently wrote this back in 1992, and ultimately, you're changing your weights based on the rewards given the glimpse that you've had, or the location of, or the selection of the image that you just referenced. So what they found when they used this model, and they used it on a couple different data sets to do classification of images, or classification of numbers, but specifically for the Street View house number data set, they compared it against a standard CNN to do classification versus using their deep recurrent attention model using the Monte Carlo policy gradient. And you can see that the actual error rate was not better just with that. So they did do a little finagling with the way they were reading and processing this actual image that helped improve the error rate. And this isn't necessarily to say it's a hard and fast, it didn't work. It's more to say, you know what, they did a pretty decent job with this, and it's starting to show some signals of how this can be very valuable. And as I mentioned earlier on, where some of the real value starts to show up especially is that, you know, the number of floating point operations are significantly less. We're talking like 80 to 90% less just using their DRAM, as well as the number of parameters, as I've mentioned, doesn't change. It doesn't change between the change in size of the image. As the image doubles in size, the parameters stay the same. This is very valuable. This can be very valuable in terms of using these models if you can use them correctly in terms of how you're going to apply them to your neural nets. So main things I want you to take away from the talk is that the attention model is allowing you to do adaptive selection. It's allowing you to provide additional context to the data you want to work with. With hard models in particular, you're able to constrain your computations. But at the end of the day, the reason why you would even consider these models is because you're trying to improve the accuracy of what you're working with the model that you're working with. I mean, that's what this is all about, right? You apply neural nets, you apply any kind of machine learning algorithm because you're trying to better predict, better pattern match whatever the problem is you're solving for. And the attention model has the potential to really help improve that solution, improve that performance. So I'd recommend checking it out. There are a number of papers that I was looking at that, like I said, came out really recently, actually. And this is, as I mentioned, already posted out there, so feel free to check it out. There are some additional references on, they're questionable in terms of the attention model, but definitely some additional resources that aren't necessarily clearly hard or soft attention models. I did have a number of people who helped me put this together, and I'm very grateful for their help. And that is all I have, except that I work with SkyMind. We are an open source deep learning platform. We're in Java and Scala. We always welcome any additional help. But more importantly, if you are interested in neural nets, and if you're new to the space especially, we have this chat channel in Gitter. It's a GitHub chat channel that you don't have to necessarily use our platform, but we have a lot of people who come out. We've got like 800 people in there right now who will chat about neural nets and share various things that they're experiencing when they're building out their models. So feel free to check it out. And thank you very much for having me for the conference. Thank you for hanging in there for this last talk. I greatly appreciate it. I hope you guys have a good night. If you have questions, find me after.